Hello there, and welcome to Beyond the Cosmos, where the biggest questions in science are explored at the pace of a slow breath, where curiosity is never rushed, and where the universe unfolds one careful thought at a time. Tonight, we are going to sit with an idea that sounds, at first, like something out of a story rather than a scientific fact. The idea that the universe, vast and rich and filled with hundreds of billions of galaxies, contains regions that are simply hostile to the existence of life. Not empty in the way a void is empty, not dark in the way the space between galaxies is dark, but actively unfavorable. Places where the raw ingredients for life may exist, where stars may shine and planets may form, and yet where something about the environment itself makes the long, patient chemistry of life unlikely or impossible. We are going to call this, tonight, the universe's dead zone, and we are going to explore it slowly, the way we explore everything here, letting each idea settle before moving to the next, building a picture of cosmic habitability that is more textured and more interesting than the simple notion that life can happen anywhere there is a star and a planet. Before we set off, I want to ask where you are right now. Perhaps you are in bed with the lights low, the day finally behind you. Perhaps you are settled into a chair, wrapped in something warm, letting your thoughts slow down. Maybe you can see a window from where you are, and beyond it, a sky with stars or clouds, or simply the orange glow of streetlight reflected off the underside of the night. Wherever you are in a place where life is not just possible but abundant, where the conditions are, by cosmic standards, remarkably gentle. Tonight, we will explore what it means that this gentleness is not guaranteed everywhere in the universe, and how astronomers have begun to map the regions where it is most at risk. If this kind of unhurried exploration of the universe helps you settle into rest, it would mean a great deal if you tapped the like button or subscribed to Beyond the Cosmos. It helps other people who are looking for a calm, thoughtful voice to think alongside find their way here. Now, let your shoulders drop, take one slow breath in and let it out without hurry. And let's begin. When we think about where life might exist in the universe, the first instinct is usually to think in terms of presence rather than absence. We ask what a planet needs to be habitable: the right distance from its star so that liquid water can exist on its surface, the right kind of star, stable and long-lived enough to allow billions of years for chemistry to do its slow work, the right chemical ingredients, carbon and oxygen and nitrogen, and the other elements that make up the molecules of life as we know it. We build up a picture of habitability by adding requirement after requirement, narrowing down the kind of place where life becomes possible. This way of thinking has given us a useful and well-known concept: the habitable zone around a star, sometimes called the Goldilocks zone, the region where a planet's surface temperature could allow liquid water to persist. It is not too close to the star, where the heat would boil any water away, and not too far, where the cold would freeze it solid. This concept has shaped decades of searches for potentially habitable exoplanets, and it remains one of the most productive ideas in modern astrobiology. But there is another way of thinking about habitability that approaches the question from the opposite direction. Instead of asking what a planet needs to have, you can ask what an environment needs to avoid. Instead of building a picture of habitability from positive requirements, you can build a picture of uninhabitability from hazards, from the kinds of cosmic violence and instability that make the patient development of life difficult or impossible, regardless of how well a planet might otherwise be positioned around its star. This second approach has led astronomers to think not just about the habitable zone of an individual star, but about a much larger structure, the habitable zone of an entire galaxy. The idea is that within a galaxy, there are regions that are more or less favorable for life, not because of anything about individual stars or planets, but because of the broader environment, the density of stars, the frequency of violent events, the amount of radiation passing through, the abundance of the heavy elements needed to build rocky planets in the first place. Tonight, we are exploring the flip side of this galactic habitable zone, the regions that fall outside it, the places, both within galaxies and beyond them, where the conditions tilt so far against the patient requirements of life that we might reasonably call them dead zones. And as we will see, the universe has several different kinds of these zones, operating at different scales for different reasons, each one revealing something important about what it actually takes for a place like Earth to exist. Let's begin close to home, with the galaxy we live in, and the question of where within the Milky Way life is most and least likely to have a fair chance. The Milky Way is not a uniform environment. Its center is utterly unlike its outskirts. The dense spiral arms are different from the quiet spaces between them. The thick disk of old stars sits differently in space than the thin disk of younger ones. Each of these regions has its own density of stars, its own rate of stellar explosions, its own background radiation level, its own chemical history. If you wanted to design an experiment to test which environments are friendly to the development of complex life, you could hardly do better than to look at the natural variation already present within a single galaxy. At the very center of the Milky Way lies the galactic bulge, a dense, roughly spherical concentration of old stars surrounding the supermassive black hole known as Sagittarius A star. This region is extraordinarily crowded. Stars are packed far more closely together than they are in our own neighborhood, and the gravitational interactions between them are correspondingly more frequent and more violent. The galactic center is also a place of extraordinary energetic activity. The supermassive black hole, even in its current relatively quiet state, occasionally flares with bursts of radiation. In the past, it is thought to have been significantly more active, producing jets and outbursts that would have bathed the surrounding region in high-energy radiation. This combination of stellar crowding and energetic violence makes the galactic center a genuinely hazardous place for the kind of long, undisturbed chemical evolution that life seems to require. A planet orbiting a star near the galactic center would face a higher risk of having its orbit disrupted by a close stellar encounter, a higher background flux of dangerous radiation, and a more chaotic overall environment compared to a planet orbiting a star out in the quieter disk of the galaxy. This is not to say that life is impossible near the galactic center. The universe rarely deals in absolutes, and the margins of habitability are an area of active scientific debate. But the balance of hazards, the density of disruptive events, tips strongly against the kind of stable, multi-billion-year window that complex life on Earth required. The galactic bulge, beautiful and ancient as it is, may be one of the universe's more inhospitable neighborhoods, a crowded downtown where the traffic of gravity and radiation makes quiet, patient development difficult. If the galactic center represents one kind of hazard, density and energetic violence concentrated in a small volume, the outer edges of the galaxy represent something like the opposite problem. Out in the far reaches of the Milky Way's disk, beyond the orbit of the Sun, the stars become progressively sparser, and a different obstacle to habitability emerges. Not too much activity, but too little of the right ingredients. This has to do with the chemistry of star formation and the slow buildup of heavy elements over cosmic time. When the universe was young, it consisted almost entirely of hydrogen and helium, the simplest elements forged in the first few minutes after the Big Bang. Every element heavier than helium, what astronomers somewhat loosely call metals, including all of the carbon, oxygen, nitrogen, silicon, and iron that make up rocky planets and living organisms, had to be manufactured inside stars and then released into space when those stars died, either gently through stellar winds or violently through supernova explosions. This means that the abundance of heavy elements in any region of a galaxy depends on how many generations of stars have lived and died there, seeding the interstellar medium with progressively richer concentrations of the elements needed for rocky planets and biochemistry. Regions of a galaxy where star formation has been active for a long time, recycling gas through generation after generation of stars, tend to be enriched in these heavier elements. Regions where star formation has been sparse, or where the gas has not been thoroughly processed, remain comparatively metal-poor, dominated still by the primordial hydrogen and helium. The outer disk of the Milky Way, and especially the diffuse stellar halo that surrounds the visible galaxy, tend to fall into this metal-poor category. Stars out there are often older, formed earlier in the galaxy's history before many generations of stellar enrichment had occurred, or they formed from gas that was never thoroughly mixed with the products of earlier stellar generations. Planets forming around these metal-poor stars face a basic raw materials problem. There may simply not be enough silicon, iron, and other elements available to build a substantial rocky planet, let alone one with the right chemistry for life. So we have, within a single galaxy, two different ways of falling outside the habitable zone. Too close to the center, where chaos and radiation dominate. Too far toward the edge, where the chemical ingredients become too sparse and too primitive. Between these two extremes lies a band, a sort of galactic Goldilocks region, where the chemistry has had enough time and enough material to enrich itself, but where the worst of the galactic center's violence has not yet reached. The Sun and the Earth sit comfortably within this band, in a quiet spiral arm roughly halfway between the crowded center and the metal-poor edge. It is worth pausing here and letting the implications of this picture settle. The fact that the Earth orbits a star in a particular, relatively favorable region of the Milky Way is not a coincidence in the sense of being completely without explanation, but it is also not something that had to be true. It reflects a combination of where and when the solar system happened to form, a combination of galactic geography and galactic history that produced, in our specific case, conditions gentle enough for billions of years of relatively undisturbed evolution. This idea that the suitability of a region within a galaxy for hosting life-bearing planets changes systematically with location and time has come to be called the Galactic Habitable Zone. The term was popularized in the early 2000s by researchers studying how the conditions for life vary not just from star to star, but across the structure of an entire galaxy. The Galactic Habitable Zone is not a fixed ring, drawn once and for all on a map of the Milky Way. It is dynamic. It has changed over the history of the galaxy and will continue to change in the future. Early in the galaxy's history, very few regions would have qualified because not enough time had passed for stellar generations to build up the necessary heavy elements anywhere. As the galaxy aged, the zone of sufficient chemical enrichment expanded outward, and the proportion of the galaxy capable of hosting potentially habitable planets grew. At the same time, the inner danger zone, the region too close to the violent and crowded center, has its own evolution. The rate of supernovae, the activity of the central black hole, and the density of stars near the bulge all change over cosmic timescales, shifting the inner boundary of safety inward or outward, depending on the era. The Galactic Habitable Zone, then, is best thought of as a region that has been slowly growing and shifting over billions of years, a band of relative safety and sufficiency expanding through the disk of the galaxy as the chemistry matures and the most violent phases of galactic youth recede into the past. We happen to have formed within that growing band, at a time and a place where the conditions had become favorable enough, but not so long ago that we are merely an early outlier, and not so recently that we represent some far future state the galaxy has only just reached. Having explored the dead zones within a single galaxy, let's expand our view outward to the scale of galaxies themselves and ask whether some entire galaxies might be more or less hospitable to life than others. This question turns out to have a rich and complicated answer because galaxies come in an enormous variety of types, sizes, and histories, and each of these variations carries implications for habitability. Consider, first, the the difference between large galaxies like our own Milky Way and the much smaller dwarf galaxies that vastly outnumber large galaxies in the observable universe. Dwarf galaxies, containing anywhere from a few million to a few billion stars, compared to the hundreds of billions in the Milky Way, face their own version of the metal poverty problem we discussed for the outer regions of our own galaxy. Because they are smaller, dwarf galaxies generally have lower overall rates of star formation and have processed less of their gas through successive generations of stars. Many dwarf galaxies remain relatively metal-poor throughout their history, meaning that even where planets do form, they may lack the heavy element abundance needed to build substantial rocky worlds. There is also the question of gravitational stability. Smaller galaxies have shallower gravitational wells, meaning that energetic events, supernova, stellar winds, and the feedback from star formation can more easily blow gas entirely out of the galaxy, rather than simply redistributing it internally, as tends to happen in more massive galaxies like the Milky Way. This means that dwarf galaxies can lose a significant fraction of the very material they need to build the next generation of enriched stars and planets, slowing their chemical evolution even further. On the other end of the size spectrum, extremely massive galaxies, the giant ellipticals that dominate the centers of large galaxy clusters, face a different set of challenges. Many of these galaxies underwent intense bursts of star formation early in their history, rapidly using up their available gas, and have since gone largely quiescent, forming few new stars in the billions of years since. A galaxy that stopped forming new stars long ago is a galaxy where the kind of younger, sun-like stars capable of providing a stable, long-lived energy source for billions of years of planetary evolution become progressively rarer over time, as the existing stellar population simply ages without replenishment. There is a kind of middle ground here too, much as there was within the disk of an individual galaxy. Spiral galaxies of roughly the Milky Way's mass, with ongoing but moderate rates of star formation, sufficient chemical enrichment built up over billions of years, and gravitational wells deep enough to retain their gas and recycle it efficiently, appear to represent something like a sweet spot for habitability at the scale of entire galaxies. Too small, and the chemistry never matures. Too large and too early forming, and the stellar population ages out of its most life-friendly phase. Beyond the question of galaxy size and type lies an even larger consideration: the environment a galaxy finds itself in, the broader cosmic neighborhood it belongs to. And here we encounter one of the more striking ideas in modern astrobiology, the notion that galaxy clusters, the densely packed cities of galaxies bound together by gravity, might themselves represent dead zones at the largest observable scales. Galaxy clusters are extraordinary environments. They contain hundreds or thousands of galaxies, bound together within a shared gravitational well embedded in a vast reservoir of superheated gas, the intracluster medium that glows brightly in X-rays at temperatures of tens of millions of degrees. This hot gas is itself a remnant of violent processes: galaxies falling into the cluster, gravitational heating, shock waves from cluster mergers, and the cumulative output of supernovae and active galactic nuclei across the cluster's long history. For a galaxy living within a rich cluster, several hazards compound. First, galaxies in clusters interact with each other and with the surrounding hot gas far more frequently than galaxies in the relative isolation of small groups or the field. These interactions can strip a galaxy of its own reservoir of cool gas, a process astronomers call ram pressure stripping, in which the galaxy's motion through the dense intracluster medium literally pushes its gas content out and away, much as wind can strip water from a sponge moving quickly through air. A galaxy stripped of its gas loses its ability to form new stars, eventually becoming what is called a red and dead galaxy, dominated by an aging stellar population with no fresh material to renew it. Second, the frequency of galaxy mergers and close encounters within a cluster environment is dramatically higher than in more sparsely populated regions of the universe. Each merger or close pass can trigger bursts of star formation, but it can also disrupt the orderly orbits of stars and planetary systems within the interacting galaxies, throwing planets out of stable configurations or exposing them to increased radiation as massive young stars form in unusual concentrations and burn through their lives quickly, ending in supernovae. Third, the central regions of rich galaxy clusters often host the most massive galaxies in the observable universe, giant ellipticals that have already exhausted much of their star-forming material, surrounded by some of the most energetic active galactic nuclei known, capable of producing jets and outbursts that can influence environments across hundreds of thousands of light years. Taken together, these factors suggest that the dense cores of rich galaxy clusters may represent a genuine large-scale dead zone, a place where the combination of gas stripping, gravitational disruption, and energetic violence makes the formation and survival of stable, life-friendly planetary systems considerably less likely than in the quieter, more isolated regions of the cosmic web. This brings us to a concept that researchers in astrobiology and cosmology have started to call, with admirable directness, the cosmic habitable age, and, in a related but distinct sense, regions of relative cosmic safety versus cosmic hazard distributed across the large-scale structure of the universe. We have already spent time, in previous explorations, with the cosmic web, the vast network of filaments, walls, clusters, and voids that defines the large-scale architecture of the universe. We now have a new lens through which to view that structure. Rather than simply asking where matter is concentrated and where it is sparse, we can ask where the conditions are gentle enough for the patient chemistry of life and where they are too violent, too sparse, or too chemically immature. The picture that emerges is one of habitability as a property not just of individual planets or stars, but of an entire hierarchy of environments, nested within each other like the layers of an onion. A planet's habitability depends on its star. A star's suitability depends on its location within its galaxy. A galaxy's suitability depends on its size, its history, and its environment. And a galaxy's environment depends on its position within the cosmic web, whether it sits in a quiet filament, an isolated void, or the crowded, violent core of a massive cluster. At every one of these scales, there are zones that favor the development of life and zones that work against it. And just as the Galactic Habitable Zone has changed over time as the Milky Way has aged and enriched itself chemically, the favorability of different environments at every scale has changed over the history of the universe. The universe as a whole is thought to have become, in some statistical sense, progressively more hospitable to life as it has aged, as more generations of stars have lived and died, enriching the cosmos with the heavy elements life requires, and as some of the most violent early phases of galaxy formation and evolution have settled into the comparatively calmer present era. This does not mean that hospitable conditions are guaranteed to increase forever. As we explored in a previous episode about the long-term fate of cosmic structure, the accelerating expansion of the universe driven by dark energy will eventually disrupt even the largest bound structures, and the supply of fresh gas available for new star formation will dwindle as galaxies exhaust and lose their reservoirs over the coming tens of billions of years. There may be a genuine peak to the universe's overall habitability, a window of maximum hospitableness that we may be living through right now, or that may still lie ahead, or that may already be behind us. This is one of the genuinely open and fascinating questions in contemporary cosmology. Let's slow down here and sit with the idea of a cosmic peak of habitability, because it is a profound thought and deserves more than a passing mention. Imagine plotting across the entire history of the universe, from the earliest moments after the Big Bang to the unimaginably distant future, a single curve representing something like the overall capacity of the universe to host life. In the earliest billions of years, this curve would be low. There simply had not been enough time for stars to manufacture and disperse the heavy elements that planets and biochemistry require. The first generation of stars, formed from pristine hydrogen and helium, could not have hosted rocky, life-bearing planets around them, because the raw materials for rocky planets did not yet exist anywhere in the universe. As the first stars lived and died, seeding the cosmos with carbon, oxygen, and the other elements forged in their cores and scattered by their deaths, the curve would begin to rise. Successive generations of stars, forming from progressively more enriched gas, would have an increasing chance of hosting planets with the right chemistry. The Milky Way and the other galaxies of the universe would have become, slowly and unevenly, more capable of producing places like Earth. Some researchers who have attempted to model this curve in detail have suggested that the peak of the universe's capacity for habitability, the time at which the largest fraction of potentially habitable planets exist, and the conditions across the universe are most favorable on average, may lie somewhere in the relatively distant future relative to the formation of our own solar system, perhaps tens of billions of years from now, long after the Sun has already died. This is an arresting thought. It suggests that, in some statistical sense, we may have arrived relatively early in the universe's habitable era rather than late. The universe may have, ahead of it, a very long future in which life becomes, on average, more rather than less likely to arise, as more galaxies enrich themselves with heavy elements, as more generations of stars complete their life cycles, and as the early violence of galaxy formation and frequent mergers settles into the calmer, more isolated future that the accelerating expansion of the universe is gradually producing. At the same time, this rising curve of habitability is itself bounded. The available gas for star formation is finite and is being consumed, lost to stellar remnants, or carried away by the relentless expansion of space. Eventually, perhaps trillions of years from now, the supply will be exhausted, star formation will cease entirely across the universe, and the long, slow fade into cosmic darkness will begin. The peak of habitability, whenever it occurs, sits between these two boundaries: an early universe too young and too chemically poor, and a far future universe too exhausted and too dark. Let's return now to the more immediate and tangible dead zones, the ones that are not about the very long arc of cosmic history, but about specific, identifiable hazards that astronomers have studied in considerable detail. One of the most dramatic of these hazards involves gamma-ray bursts, among the most energetic explosions known to occur anywhere in the universe. A gamma-ray burst is an intensely focused beam of high-energy radiation released over a period ranging from a fraction of a second to several minutes, thought to be produced either by the collapse of a massive, rapidly rotating star into a black hole, or by the merger of two extremely dense stellar remnants such as neutron stars. The energy released in a single gamma-ray burst, concentrated into a narrow beam, can briefly outshine the combined light of every other source in its host galaxy, despite originating from a region no larger than a star. If a gamma-ray burst were to occur close enough to Earth, and if its narrow beam happened to be pointed in our direction, the consequences could be severe. The intense burst of gamma radiation and the secondary effects it would produce in Earth's atmosphere, including the destruction of a significant fraction of the ozone layer, could expose the surface to dramatically increased levels of harmful ultraviolet radiation from the Sun for months or years afterward, with potentially serious consequences for many forms of life, particularly in the oceans where much of the biosphere's productivity depends on organisms vulnerable to ultraviolet damage. This has led some researchers to propose that gamma-ray bursts may have been responsible for at least one of the major extinction events in Earth's deep history, and more broadly, that the frequency of gamma-ray bursts in a given region of the universe is an important factor in determining how hospitable that region is to the long-term survival of complex life. A planet that might otherwise sit comfortably within a galaxy's habitable zone could nonetheless face a heightened risk of catastrophic sterilization if it happens to lie in a part of the galaxy or a part of the universe more broadly, where gamma-ray bursts occur with greater frequency. And here is where the dead zone concept becomes genuinely interesting at a cosmic scale, because the rate of gamma-ray bursts is not uniform across the universe or across cosmic time. Long gamma-ray bursts, associated with the collapse of massive stars, are thought to occur preferentially in galaxies with relatively low abundances of heavy elements, because metal-poor massive stars retain the rapid rotation needed to produce the kind of collapse that generates a burst, while metal-rich stars tend to lose angular momentum through stellar winds before they die. This means that gamma-ray bursts were likely far more common in the early universe, when galaxies were generally more metal-poor, and have become progressively rarer as the universe has aged and chemically enriched itself. Some researchers have gone so far as to suggest that the early universe may have been almost uniformly hostile to complex life because of the sheer frequency of gamma-ray bursts capable of sterilizing entire regions of a galaxy, and that only in the more chemically mature, gamma-ray burst quieter universe of the past few billion years has life had a realistic opportunity to develop and persist over the long timescales required for complexity to emerge. Gamma-ray bursts are dramatic, but they are not the only cosmic hazard that astronomers have identified as contributing to the patchwork of dead and living zones across the universe. Another significant hazard, closer to home in a sense, involves the supernovae produced by ordinary massive stars at the end of their lives. A supernova, the explosive death of a massive star, releases an enormous amount of energy, including a burst of high-energy radiation and a wave of charged particles that expand outward through interstellar space for thousands of years afterward. While a single supernova does not approach the destructive power of a gamma-ray burst, it does not need to. Supernovae are far more common, occurring at a rate of perhaps 1 or 2 per century within a galaxy like the Milky Way, and their effects, while less extreme than a gamma-ray burst, can still be significant if a star and its planets happen to be superly close to the explosion. Researchers studying this hazard have generally concluded that a supernova occurring within roughly 30 light-years of a planet could deliver enough radiation to cause serious damage to that planet's atmosphere and biosphere, again, primarily through the destruction of protective ozone and the resulting increase in surface ultraviolet exposure. Though the precise distance at which danger becomes significant depends on the details of the supernova and the structure of the planet's atmosphere and magnetic field. This means that the local density of massive, short-lived stars in any given region of a galaxy is directly relevant to that region's habitability. Regions with a high concentration of young, massive stars, the kind found in active star-forming regions and spiral arms, carry an elevated risk of relatively close supernova over the timescales relevant to the development of complex life. Regions with fewer massive stars, more typical of the quieter interarm regions of a spiral galaxy, carry correspondingly lower risk. There is an interesting wrinkle here related to the orbital motion of stars like our own Sun around the galaxy. The Sun does not sit in a fixed position relative to the spiral arms of the Milky Way. As it orbits the galactic center, it periodically passes through regions of higher stellar density, including, on occasion, the spiral arms themselves, where star formation and the associated supernova rate are elevated. Some researchers have speculated that passages through or near spiral arms might correlate with increased rates of nearby supernovae, and have looked for correlations between these galactic passages and patterns in Earth's biological and climatic history, though this remains an active and somewhat contested area of research rather than a settled conclusion. What is reasonably well established is the basic principle. Regions of a galaxy with a higher density of recent and ongoing massive star formation carry a correspondingly higher background risk of nearby supernovae, and this risk is one of the factors, alongside chemical enrichment and overall stellar density, that determines how favourable any given galactic neighbourhood is for the long-term, undisturbed development of life. There is another category of dead zone worth exploring, one that operates not through sudden violence, but through a slower, more persistent kind of hazard. The steady background hum of cosmic radiation itself, and how its intensity varies across different environments in the universe. Cosmic rays, the extremely high-energy particles, mostly protons and atomic nuclei, that travel through space at velocities approaching the speed of light, are produced by a variety of sources, including supernova remnants, active galactic nuclei, and other energetic astrophysical processes. They constitute a constant, low-level radiation hazard throughout the galaxy, one that planets are partially protected from by their magnetic fields and atmospheres, but that nonetheless represents an ongoing background level of biological risk, particularly to organisms living in environments without thick atmospheric or magnetic shielding. The intensity of this cosmic ray background is not uniform. It is elevated near regions of active star formation, near supernova remnants, and near the energetic environments associated with active galactic nuclei. It is comparatively lower in quieter regions of a galaxy's disk, far from recent supernovae and away from the more turbulent, energetic galactic center. This adds another dimension to our picture of galactic habitability. A region might be chemically well enriched, sufficiently distant from the violent galactic center, and not currently at elevated risk from a nearby gamma-ray burst or supernova, and yet still experience an elevated long-term cosmic ray background simply because of its proximity to multiple sources of high-energy particles accumulated over a long period. Habitability, in this sense, is not a single hazard to avoid, but a composite of many overlapping risks, each with its own spatial pattern that together determine the overall favorability of any given location. There is a particularly interesting connection here to the question of a planet's atmosphere and its long-term stability. Some researchers studying the relationship between cosmic ray flux and atmospheric chemistry have proposed that elevated cosmic ray exposure by ionizing atmospheric molecules could play a role in cloud formation and atmospheric chemistry in ways that might influence a planet's climate over geological timescales. The science here remains actively debated, and the magnitude of any such effect on Earth's own climate history is uncertain. But the broader principle illustrates how thoroughly intertwined the question of habitability is with the surrounding galactic and cosmic environment, far beyond the simple matter of a planet's distance from its star. All of the hazards we have discussed so far, gamma-ray bursts, supernovae, cosmic rays, gas stripping, gravitational disruption, point toward dangerous concentrations of energy and activity. But there is another, quite different way for a region of the universe to become a dead zone, not through too much activity, but through too little. Through emptiness so profound that the basic raw materials for life simply are not present in sufficient quantity, regardless of how calm and undisturbed the environment might otherwise be. We have, in previous episodes, explored the great cosmic voids, the vast, underdense regions of the universe, hundreds of millions of light-years across, where the density of galaxies drops to a small fraction of the cosmic average. These voids represent, in a sense, the ultimate quiet neighborhoods of the universe. Free from the violent crowding of galaxy clusters, free from the energetic chaos of galactic centers, the interior of a void offers about as peaceful and undisturbed an environment as the universe has to offer. And yet, this very peacefulness comes at a steep cost. The handful of galaxies that exist within the great cosmic voids tend to be sparse, isolated, and often chemically underdeveloped compared to galaxies embedded in richer environments. With fewer close neighbors to trigger gravitational interactions and the associated bursts of star formation that drive chemical enrichment, and with the available gas more thinly spread, void galaxies often retain a more primitive chemical composition for longer, taking more cosmic time to build up the heavy element abundances needed for substantial rocky planet formation. This creates an intriguing tension at the heart of the void environment. It is, in terms of violent hazards, one of the safest places in the universe. No nearby gamma ray bursts to fear, in any statistical sense, no crowded cluster cores stripping gas and disrupting orbits, no dense concentrations of massive stars producing frequent supernovae. And yet, the very isolation that produces this safety also slows the chemical maturation that life ultimately depends on. A planet forming deep within a cosmic void might face a long wait before its host galaxy has produced enough heavy elements for that planet to even exist as a substantial rocky world, let alone host the complex chemistry of life. In this sense, the great voids occupy an interesting and somewhat paradoxical position in our map of cosmic habitability. They are simultaneously among the safest and among the most chemically impoverished environments in the observable universe. Whether this nets out, on balance, to a favorable or unfavorable environment for the eventual emergence of life is a genuinely open question, and one that depends sensitively on the relative importance of violent hazards versus chemical maturity in determining a planet's ultimate prospects. Let's bring this back, for a moment, to scale, because it is easy, when discussing dead zones and habitable zones at the level of galaxies and cosmic voids, to lose track of just how enormous these structures are and how the concept of habitability stretches and adapts as it moves from the scale of a single planet to the scale of the observable universe. A planetary habitable zone, the traditional Goldilocks zone around an individual star, might span a region only a fraction of an astronomical unit wide, a sliver of space measured in tens of millions of kilometers. A galactic habitable zone, the band within a galaxy's disk where chemical enrichment is sufficient and violence is minimized, spans thousands of light-years, a region so large that crossing it at the speed of light would take longer than the entire span of recorded human history many times over. A void, the largest and most chemically impoverished kind of dead zone we have discussed, spans hundreds of millions of light-years, a region so vast that the light from one side has not yet had time to reach the other since the void began forming billions of years ago. And the question of the universe's overall peak habitability across cosmic time spans the entire history of the cosmos, from the first fraction of a second after the Big Bang to a future so distant that the stars themselves will have, by then, mostly burned out. Each of these scales operates by its own logic, with its own characteristic hazards and its own characteristic requirements. And yet they are connected, nested within each other, each one setting the broader context within which the next, smaller scale operates. A planet's fate depends on its star. Its star's fate depends on its galactic neighborhood. That neighborhood's fate depends on the galaxy's overall history and structure. and the galaxy's fate depends on its place within the cosmic web, whether it sits in an isolated void, a quiet filament, or the crowded heart of a massive cluster. Holding all of these scales in mind simultaneously is part of what makes this subject so rich, and also part of what makes it so difficult to summarize with a single simple statement about where in the universe life is likely or unlikely to exist. The universe does not have one dead zone. It has many, nested within each other, operating at vastly different scales, shaped by vastly different physical processes, and each one telling its own part of the larger story about what it takes for a place like Earth to come into being and to persist. Having surveyed the landscape of cosmic dead zones at multiple scales, it is worth turning our attention to a related and equally fascinating question. What does the existence of these zones tell us about our own situation here on Earth, in the Milky Way, in the present era of cosmic history? The Earth sits in what appears, by the criteria we have discussed, to be a remarkably favourable location. We are far enough from the galactic centre to avoid its worst hazards, but not so far out toward the edge that our solar system formed from chemically impoverished material. We orbit a star in a relatively quiet interarm region of the galaxy's disk, away from the most active and dangerous concentrations of massive short-lived stars, though our solar system has likely passed through or near spiral arms multiple times over its history. We exist in an era of the universe's history roughly 9 billion years after the Big Bang for the formation of the solar system, and now closer to 14 billion years after the Big Bang, when several generations of stars have already lived and died, enriching the galaxy with the heavy elements our planet and our bodies are built from, but before the long, slow decline of star formation has progressed too far. We are also fortunate in terms of larger cosmic structure. The Milky Way sits not in the crowded, hazardous core of a massive galaxy cluster, but in a relatively modest group of galaxies, the local group itself situated on the outskirts of the larger Virgo supercluster and the still larger Laniakea supercluster we explored in a previous episode. We are far from the violent environment of a cluster core, far from the gas stripping and gravitational disruption that characterizes those dense environments, and yet not so isolated as to be trapped in the chemically slow development of a deep cosmic void. In other words, across nearly every scale we have examined tonight, from the immediate galactic neighborhood of the solar system to the largest cosmic structures the Milky Way belongs to, our circumstances appear to sit comfortably within the range of conditions favorable to the long, patient development of complex life. This is not a coincidence in the sense of being inexplicable. It reflects, in part, a selection effect. We would not be here asking these questions in an environment too hostile for life to have developed and persisted over billions of years. But it is also, in another sense, a remarkable convergence, a stacking of favorable conditions across many different scales, each one independently capable of disrupting the whole if it had gone differently. This convergence of favorable conditions across multiple scales touches on a deeper question that has occupied philosophers and scientists alike, sometimes discussed under the heading of the anthropic principle, or, in a related but distinct framing, the question of cosmic fine-tuning for habitability. The basic observation is this: if any one of the conditions we have discussed tonight had been significantly different in a way that made our particular corner of the universe less favorable, then the development of observers capable of studying and discussing these very questions would have been correspondingly less likely. If the solar system had formed too close to the galactic center, or in a galaxy too small to retain sufficient gas for chemical enrichment, or within the crowded and violent core of a rich galaxy cluster, the long, undisturbed timescales that complex life appears to require might never have materialized. This observation can be interpreted in different ways, and the differences matter for how we understand our own situation. One interpretation treats this convergence of favorable conditions as essentially a matter of statistics across an enormous number of possible locations. Given the vast number of stars, planets, and galaxies in the observable universe, even if only a small fraction of locations are favorable for the long development of complex life, the sheer number of possible locations means that some of them will, simply by chance, find themselves in a favorable spot. We happen to be examples of life that arose in one of those favorable spots, and our perspective on the universe is necessarily filtered through that fact. We could not observe the universe from an unfavorable location, because life capable of observation would not have had the chance to develop there. A different but related interpretation emphasizes the active, ongoing nature of cosmic habitability as something that changes over time, as we discussed earlier in the context of the universe's habitability curve. Rather than treating our location as a fixed, lucky draw from a vast lottery of possible places, this view emphasizes that the universe itself has been becoming, on average, progressively more hospitable as it ages and chemically matures, and that we represent one of the relatively early instances of life arising during this gradual transition from a young, violent, chemically poor cosmos to a more settled, more enriched one. Both of these perspectives are scientifically reasonable, and they are not necessarily in conflict with each other. They simply emphasize different aspects of the same underlying reality: that habitability, far from being a simple binary property that a location either has or lacks, is a graded, evolving, multi-scale phenomenon shaped by an enormous number of interacting factors, and that our own existence represents one particular, specific outcome of that complex and ongoing process. There is a thought experiment that researchers sometimes use to make the scale of cosmic habitability more concrete, and it is worth walking through slowly tonight because it helps connect the abstract discussion of dead zones and habitable zones to something a little more tangible. Imagine taking the entire volume of the observable universe and dividing it into regions according to their relative favorability for the long-term development of complex life, using the criteria we have discussed: chemical enrichment, distance from violent galactic centers, frequency of nearby supernovae and gamma-ray bursts, membership in or proximity to dense galaxy clusters, and overall cosmic ray background. You would not get a simple map with sharply defined boundaries between safe and dangerous zones. You would get something far more textured, a gradient of favorability that varies continuously across multiple overlapping scales, with some regions favorable on one criterion but unfavorable on another. A planet orbiting a sun-like star in a quiet, chemically enriched spiral arm of a Milky Way-sized galaxy, itself sitting in a modest galaxy group far from the crowded core of a massive cluster, would score favorably across nearly every criterion we have discussed. This describes, of course, our own situation reasonably well. A planet orbiting a similar star, but located within the dense, chemically impoverished outskirts of a small dwarf galaxy deep within a vast cosmic void, would face the chemical poverty problem we discussed earlier, even while benefiting from a relatively low background hazard from supernovae and gamma-ray bursts due to the overall sparseness of its surroundings. A planet orbiting a star near the crowded center of a galaxy similar to our own, even if otherwise well-positioned, would face an elevated risk from stellar crowding, gravitational disruption, and the energetic activity of the central supermassive black hole. And a planet orbiting a star within the core of a rich galaxy cluster would face the compounding hazards of ram pressure gas stripping, frequent galaxy interactions, and proximity to some of the most energetic active galactic nuclei in the observable universe. Mapping the universe this way, By overlaying these different criteria across the full range of cosmic environments, gives us something like a three-dimensional, time-evolving topography of habitability, with peaks of relative favorability and valleys of relative hostility distributed throughout the cosmic web. We happen to live near one of the peaks, but the existence of the valleys, the dead zones, tells us something important: that the conditions allowing for a planet like Earth to exist and for life to develop and persist over billions of years are not the universal default state of the cosmos, but a specific, identifiable, and in some sense fragile combination of circumstances. Let's turn our attention now to a particular and especially striking example of a galactic dead zone that has received considerable scientific attention. The environment surrounding active galactic nuclei, the supermassive black holes at the centers of many galaxies that are, at least episodically, consuming material and releasing enormous amounts of energy in the process. We mentioned the relatively quiescent black hole at the center of our own Milky Way earlier, noting that it occasionally flares, but is, in its current state, far less energetic than it could be. Many other galaxies, however, host central black holes that are far more active, accreting material at much higher rates and producing correspondingly more dramatic effects on their surroundings. These actively accreting supermassive black holes power what astronomers call active galactic nuclei, and in their most extreme forms, quasars, some of the most luminous and energetic objects in the observable universe. The energy released by an active galactic nucleus can take several forms, including intense radiation across the electromagnetic spectrum and, in many cases, powerful jets of charged particles accelerated to relativistic speeds and beamed outward from the poles of the black hole's accretion disk. These jets can extend for hundreds of thousands of light years, far beyond the visible extent of the host galaxy itself, carrying enormous amounts of energy into the surrounding intergalactic medium. A planet orbiting a star within a galaxy hosting a highly active galactic nucleus would face a substantially elevated radiation environment, particularly if that planet happened to lie within or near the path of one of the energetic jets. Even outside the direct path of a jet, the overall radiation output of a quasar-class active galactic nucleus can be high enough to influence conditions across a significant fraction of its host galaxy, potentially stripping away protective atmospheric layers on planets that might otherwise be well positioned for habitability based on their distance from their own host star alone. The good news, from the perspective of life's prospects, is that the most extreme phase of quasar activity in the universe's history occurred relatively early, when galaxies were younger and had larger reservoirs of gas available to feed rapid accretion onto their central black holes. The quasar era, as it is sometimes called, peaked several billion years after the Big Bang and has been declining in overall intensity and frequency ever since, as the universe has aged and the easily accessible gas supply feeding these central black holes has diminished. The Milky Way's own central black hole, relatively quiet in the present era, may well have gone through a more active phase earlier in the galaxy's history, a phase that, fortunately for the eventual development of life on Earth, occurred before our solar system and our planet had formed. This adds yet another temporal dimension to our picture of cosmic dead zones. Galaxies that might be relatively hospitable today could have been considerably less so in the past, during a more active phase of central black hole accretion, and the timing of a planet's formation relative to its host galaxy's history of nuclear activity is one more factor determining its overall prospects for hosting long-term, undisturbed biological development. There is a particularly evocative and somewhat haunting concept in this area of research that deserves its own moment of attention. The idea of a galaxy experiencing what astronomers sometimes informally call a sterilization event, a period during which conditions across a large fraction of the galaxy become temporarily or even permanently hostile to the persistence of life, even on planets that might otherwise be well positioned. A sufficiently energetic event at a galaxy's center, whether from a dramatic flare of activity from the central black hole or from an unusually intense and clustered episode of supernova activity in the central regions, could in principle release enough radiation to significantly damage the atmospheres and biospheres of planets across a substantial portion of the galaxy's disk. Not just in the immediate vicinity of the event, but at distances of many thousands of light years, depending on the intensity and duration of the outburst. Some researchers have speculated that such events, while rare, may have occurred periodically throughout the history of large galaxies like our own, potentially resetting the clock on biological development across wide swaths of the galactic disk each time they occur. If true, this would mean that the patient, multi-billion-year process required for complex life to emerge has not just been a matter of finding a favorable location within the galaxy, but also a matter of timing, of a planet happening to exist during a sufficiently long interval between major sterilizing events for its biosphere to develop and mature without being catastrophically interrupted. This is, it must be said, a more speculative area of research than some of the other hazards we have discussed tonight, and the frequency, intensity, and galaxy-wide reach of such hypothetical sterilization events remain genuinely uncertain and actively debated among researchers. But the concept itself is valuable for the way it reframes our thinking about habitability, shifting the emphasis from a purely spatial question, where in the galaxy is it safe, to a combined spatial and temporal question, where and when in the galaxy's history has it been safe for long enough. Earth's own unbroken, roughly 4 billion-year history of continuous biological development, even through several dramatic mass extinction events caused by more local and modest hazards like asteroid impacts and volcanic activity, suggests that our particular corner of the Milky Way has, fortunately, avoided any galaxy-wide sterilizing catastrophe throughout the entire span of life's existence here. Whether this reflects good fortune, a genuinely low background rate of such events in our particular galactic environment, or some combination of both, remains an open and fascinating question. Let's shift our attention now to thinking about how this picture of cosmic dead zones connects to the broader search for life beyond Earth, and particularly to the question of where astronomers searching for potentially habitable exoplanets should be looking, and where they might reasonably expect to find fewer promising candidates. The vast majority of exoplanets discovered to date have been found around stars relatively close to our own solar system, simply because nearby stars are easier to observe in the detail required to detect orbiting planets. This means that our current catalogue of known exoplanets is heavily biased toward our own galactic neighborhood, a region we have already identified as sitting comfortably within the favorable band of the Galactic Habitable Zone. We have not yet been able to systematically survey planets closer to the galactic center in the metal-poor outer halo or in other, more distant galaxies to see how the frequency of potentially habitable worlds changes as we move into less favorable regions. This is changing gradually as observational techniques improve and as missions specifically designed to survey larger and more diverse stellar populations come online. Future surveys may be able to test, in a much more direct and statistically robust way, the predictions of the Galactic Habitable Zone concept by comparing the frequency of potentially habitable, rocky exoplanets in chemically enriched, quiet regions of the galaxy's disk against their frequency in more hazardous regions closer to the galactic center or in more metal-poor regions further out. There is also growing interest in studying the exoplanet populations of other types of galaxies, comparing what is found in spiral galaxies like our own against dwarf galaxies, against galaxies with more active central black holes, and eventually, as instruments improve, against galaxies embedded in different large-scale environments, from isolated voids to crowded cluster cores. Each of these comparisons offers a way to test, with real observational data, the theoretical picture of cosmic dead zones and habitable zones that we have been exploring tonight. This is one of the genuinely exciting frontiers of contemporary astrobiology. The gradual transition from a largely theoretical understanding of how habitability might vary across different cosmic environments, built up from our understanding of stellar physics, galactic chemistry, and cosmic violence, toward an empirical, observationally grounded picture built from the actual census of exoplanets found in different environments. We are, in a sense, beginning to test the map of cosmic dead zones we have sketched tonight against the real distribution of planets the universe has actually produced. As we continue moving through this exploration, it is worth pausing to consider a particular and somewhat counterintuitive wrinkle in the story of cosmic dead zones. The possibility that some environments we might initially assume to be hostile to life could, under certain circumstances, turn out to be more favorable than expected, or vice versa, and how this complicates any simple, confident map of where life is and is not likely to be found. Consider, for instance, the dense stellar environments of globular clusters, the tightly packed ancient spherical collections of stars, often containing hundreds of thousands of individual stars within a volume only a few dozen light-years across, that orbit within the halos of galaxies like our own. At first glance, these seem like obvious dead zones. The stellar density is extraordinarily high, meaning that close gravitational encounters between stars capable of disrupting planetary orbits would be far more frequent than in the relatively spacious environment of our own solar neighborhood. Globular clusters are also generally composed of old, metal-poor stars formed early in the galaxy's history before much chemical enrichment had occurred, suggesting limited prospects for substantial rocky planet formation. And yet, some researchers have pointed out a potential silver lining specific to globular cluster environments. The extraordinarily high density of stars means that even if any individual star has a low probability of hosting a habitable planet, the sheer number of stars packed into a small volume could mean that a globular cluster contains a non-negligible total number of potentially habitable worlds, simply due to the statistics of large numbers, even if the per-star probability is unusually low. Additionally, the close proximity of stars within a globular cluster means that any planet capable of supporting an advanced civilization would find traveling to neighboring star systems dramatically easier than it would be in our own comparatively sparse galactic neighborhood, a consideration relevant to the search for technologically advanced extraterrestrial life specifically, even if it does not change the underlying biological hazards. This kind of nuance, where a naive first assessment of an environment's habitability can be complicated or even partially reversed upon closer examination, is a recurring theme in this area of research, and it serves as a useful reminder that the map of cosmic dead zones we have been building tonight, while grounded in solid physical principles, remains in many respects a work in progress, with new considerations and complications continuing to emerge as researchers examine each type of environment in greater depth. There is another subtlety worth exploring before we draw our reflections together tonight, and it concerns the difference between conditions favorable for the origin of life and conditions favorable for the long-term persistence and increasing complexity of life once it has already begun. Much of our discussion tonight has implicitly assumed that these two requirements track each other closely, that an environment favorable for life to begin is also favorable for that life to persist and develop in complexity over billions of years. In broad terms, this assumption is probably reasonable. An environment with fewer violent disruptions and a more stable chemical and radiative background is likely to be favorable for both the initial emergence of life and its subsequent long-term flourishing. But it is worth noting that these two questions, the origin of life and the persistence of life, may have somewhat different requirements in detail, and the relative importance of different hazards may shift depending on which question we are asking. Some researchers studying the origin of life have proposed that certain kinds of environmental energy input, perhaps including elevated levels of certain forms of radiation or the chemical disequilibrium created by violent events, might actually have played a constructive role in the very earliest chemical steps toward life, providing the energy needed to drive the formation of complex organic molecules from simpler precursors, even while the same kinds of energetic events would be uniformly destructive to an already established complex biosphere. This raises the intriguing and still largely unresolved possibility that the ideal environment for the origin of life might differ, at least in degree, from the ideal environment for the subsequent billions of years during which that life needs a stable, undisturbed environment in which to develop increasing complexity. A region with a moderate, rather than minimal, level of background hazard might, in principle, offer the best balance, sufficient energetic disequilibrium to kickstart the chemistry of life, followed by sufficient subsequent calm for that life to mature and diversify without being repeatedly and catastrophically disrupted. This remains a genuinely speculative area of research, and we do not yet have anything like a settled answer to the question of what the truly optimal environmental history looks like for the full journey from prebiotic chemistry to complex, perhaps even intelligent, life. But it adds one more layer of richness and uncertainty to our map of cosmic habitability, reminding us that the dead zones and habitable zones we have been discussing tonight are not simple, static labels, but are themselves shaped by deep and still partially unanswered questions about the actual chemical and physical pathway from non-life to life, and from simple life to complex life. Let's take a moment now to step back from the specific hazards and mechanisms we have explored and think more broadly about what this entire picture of cosmic dead zones tells us about the nature of the universe and our place within it. The universe, on its largest scales, is often described accurately as vast beyond comprehension, containing hundreds of billions of galaxies, each with hundreds of billions of stars, each potentially hosting planets of its own. Faced with numbers this large, it is tempting to assume that life, if it is possible at all, must be common simply because there are so many opportunities for it to arise somewhere among such an enormous number of candidate locations. What our exploration tonight suggests is a more nuanced picture. Yes, the universe is enormous, and yes, the raw number of stars and planets is staggering. But the universe is not uniformly favorable to the long, patient development of life. It is structured, textured, full of regions that are actively hostile for one reason or another, alongside the regions that are favorable. The vast majority of locations in the universe, when judged against the multiple criteria we have discussed tonight, chemical enrichment, distance from violent galactic centers, frequency of nearby supernovae and gamma-ray bursts, membership in or proximity to crowded cluster environments, may turn out to be considerably less favorable than the specific location the Earth happens to occupy. This does not mean that life is necessarily rare in the universe. The sheer number of stars and planets is large enough that even a relatively small fraction of favorable locations could still translate into an enormous absolute number of potentially habitable worlds scattered throughout the cosmos. But it does suggest that finding those favorable worlds may require looking in the right places, understanding which regions of which galaxies, embedded in which kinds of larger cosmic structures, are most likely to have produced the kind of long, undisturbed, chemically rich environment that complex life appears to require. In this sense, mapping the universe's dead zones is not a pessimistic exercise, a catalogue of places where life cannot exist, so much as it is a refinement of our search, a way of focusing our attention and our limited observational resources on the regions of the universe most likely to reward careful investigation. The dead zones, paradoxically, help illuminate the living zones by contrast, helping us understand exactly what it is about our own corner of the cosmos that has allowed it to become, against a backdrop of violence and chemical poverty, stretched across most of the universe's volume. A place where something as intricate and improbable as a thinking, observing creature could come into being. As we begin to bring this long exploration toward its close, it is worth returning one more time to the specific, concrete reality of where we are. Here, now, on this particular planet, in this particular galaxy, at this particular moment in cosmic history. We have spent this evening traveling through the violent, crowded heart of the Milky Way, through the chemically impoverished outer halo, through the crowded and hazardous cores of rich galaxy clusters, through the energetic jets of active galactic nuclei, through the long, slow arc of the universe's overall chemical enrichment from the earliest moments after the Big Bang to a hypothetical far future peak of habitability, and through the vast, quiet, chemically primitive emptiness of the great cosmic voids. And at the end of all of this traveling, we arrive back where we started. A quiet, modestly sized spiral galaxy situated in an unremarkable but comfortably favorable spiral arm, orbiting at a comfortable distance from a crowded and violent galactic center, chemically enriched by billions of years of prior stellar generations, situated within a modest galaxy group on the outskirts of a large supercluster far from the crowded and hazardous core of any rich galaxy cluster, existing at a moment in cosmic history roughly 9 billion years after the universe's hottest and most chemically immature early period, and roughly equally far from whatever far future peak of cosmic habitability may yet lie ahead. This is, by any reasonable accounting, a fortunate address. Not the only possible fortunate address in the universe, almost certainly, given the sheer scale of the cosmos and the large number of locations that likely share at least some of these same favorable characteristics. But a fortunate address nonetheless, and one whose favorability becomes considerably more apparent and considerably more meaningful once you have spent some time, as we have tonight, exploring the alternative. The many ways, at many different scales, that the universe could have been, and in most places actually is, considerably less hospitable than the specific neighborhood we happen to call home. There is a particular kind of gratitude that can emerge from this kind of exploration, one that is worth sitting with gently as we move toward the close of tonight's journey. It is easy, in the ordinary course of daily life, to take for granted the basic fact of a stable, life-supporting environment. The fact that the ground does not regularly shake with violence beyond what our planet's own geology produces, that the sky does not periodically deliver lethal doses of radiation from some catastrophic galactic event, that the chemistry of our world has had billions of years of quiet, undisturbed time in which to develop the intricate complexity that life requires. These are not universal features of existence in the cosmos. They are specific, identifiable, and in some real sense fortunate features of our particular corner of an otherwise vast and frequently hostile universe. This is not a thought meant to induce anxiety about how things might have been different. Quite the opposite. It is a thought meant to deepen the sense of quiet appreciation for how things actually are. The universe has produced in our specific location a remarkably stable and gentle environment sustained over billions of years. against a backdrop of violence and chemical poverty that characterizes much of the rest of the cosmos. That stability and gentleness is not something we earned or chose. It is something we inherited, a gift handed down through billions of years of cosmic history, through the specific, fortunate sequence of events that placed our solar system where and when it formed. Carrying that knowledge, gently, without anxiety, as a quiet background awareness rather than an urgent preoccupation, can add a particular texture to the ordinary experience of being alive on this particular planet. The ground beneath you is stable, not because stability is the universe's default condition, but because, in this specific place, at this specific time, the multiple layers of cosmic hazard we have explored tonight have, for billions of years, remained sufficiently distant and sufficiently rare to allow life to develop, undisturbed, into the rich complexity it has achieved here on Earth. Let's spend a few final moments considering what all of this might mean for the future, both the near future relevant to human concerns and the far future relevant to the deep history of the universe itself. In the near term, understanding the structure of cosmic dead zones and habitable zones has practical implications for the ongoing search for life elsewhere in the universe. As we discussed, future surveys aimed at characterizing the distribution of potentially habitable exoplanets across different galactic environments will be able to test, with real data, the theoretical picture we have built tonight. If the Galactic Habitable Zone concept holds up under this kind of empirical scrutiny, it will provide astrobiologists with a powerful tool for prioritizing where to focus the substantial resources required for detailed exoplanet characterization, directing attention toward the regions of the galaxy and eventually other galaxies, most likely to harbor genuinely habitable worlds. In the longer term, the same considerations that determine the favorability of different cosmic environments for the origin and persistence of life also bear on questions about the very long-term future of life here on Earth, and of any civilization that might eventually expand beyond our home planet. Understanding which regions of the galaxy carry elevated long-term risk from supernovae, gamma-ray bursts, or other catastrophic events could, in principle, inform extremely long-term thinking about where a spacefaring civilization might choose to expand, or which regions might warrant particular caution. And, at the very longest timescales, the gradual evolution of the universe's overall habitability, the slow rise from the chemically poor and violent early universe toward whatever peak of habitability may lie in the distant future, and the eventual decline as star formation exhausts the available gas supply across the cosmos, offers a kind of ultimate context for thinking about the place of life, including our own, within the full arc of cosmic history. We exist at a particular moment within that arc, neither at its beginning nor, very likely, at its end, participating in a universe that has been becoming in fits and starts across billions of years and countless individual environments, progressively more capable of producing and sustaining the kind of complexity that life represents. As the night settles further and the weight of sleep begins to gather, let's hold one final image in mind, drawing together the many threads we have followed tonight. Picture the universe not as a uniform field of stars, scattered evenly and indifferently through space, but as a vast, textured landscape with peaks of habitability and valleys of hostility distributed across every scale, from the immediate neighborhood of individual stars up through the structure of entire galaxies and the largest superclusters of the cosmic web. Picture this landscape changing slowly over billions of years. The early universe a largely hostile terrain of chemical poverty and violent youth, gradually softening and enriching itself as generation after generation of stars completed their lives and seeded the cosmos with the elements life requires, even as new hazards, the most active phases of galactic nuclei, the densest concentrations of cluster environments, carved their own valleys of hostility into different parts of the landscape at different times. And picture, somewhere within this vast and shifting terrain, a small, modest peak formed in a quiet spiral arm of an ordinary galaxy, far from the crowded and dangerous center, far from the chemically impoverished edge, far from the violent core of any rich galaxy cluster, sitting instead in the calm outskirts of a modest galactic neighborhood, enriched by billions of years of prior stellar generations, undisturbed by any galaxy-wide catastrophe for the entire multi-billion-year history of life's development there. That peak is where you are right now. Not metaphorically, but literally in the most direct and physical sense the language allows. You are, at this moment, located within one of the universe's relatively rare and relatively favorable regions, a place where the long, patient, improbable chemistry of life has had the chance, across billions of years, to develop into the rich complexity that allows for a planet full of living things, including creatures capable of looking outward, mapping the hazards of the wider cosmos, and understanding with real scientific precision just how fortunate their particular address actually is. The universe has a dead zone. In truth, it has many, nested within each other, distributed across every scale we have explored tonight. And against that vast backdrop of cosmic hostility, scattered with rare and precious exceptions, you happen to occupy one of those exceptions. Not through any choice or effort of your own, but through the long, patient unfolding of cosmic history that placed a quiet, modest, comfortably enriched corner of the universe exactly where it needed to be, for exactly long enough for you to exist and to rest. Here, now, safely within it. If tonight's slow journey through the universe's hidden topography of hazard and safety has given you something to settle into, some quiet sense of how fortunate your own small corner of the cosmos actually is, you are welcome to return to Beyond the Cosmos whenever you would like to explore further. There is always another layer to this landscape, always another scale at which the universe reveals its texture, its history, and its quiet, ongoing structure. For now, let the weight of the day finally release. Let the image of the universe's vast, uneven landscape of habitability settle gently into the background of your mind, not as a source of worry, but as a source of quiet wonder at how specific, how particular, and how genuinely fortunate your own existence within that landscape actually is. The dead zones are out there, vast and largely indifferent, scattered across every scale of the cosmos. And here, in this small, quiet, comfortably favorable corner of it all, you are safe. You are home. You are exactly where the universe, after billions of years of patient unfolding, needed you to be. Good night. Let's go back, for a while, to the question of timing, because there is a temporal dimension to the story of cosmic dead zones that deserves a more thorough exploration than we have given it so far. And it concerns the very early universe in particular, a period sometimes called the Cosmic Dark Ages, though the term is used in a different sense than the dead zones we have been discussing tonight. In the first few 100 million years after the Big Bang, before the first stars and galaxies had formed, the universe was filled with a diffuse sea of neutral hydrogen and helium gas, expanding and cooling, but not yet organized into the structures we recognize today. There were no stars to provide light, no heavy elements to build planets, and certainly no possibility of life as we understand it. This period, before the first generation of stars ignited, represents the most extreme and most universal dead zone the cosmos has ever known. A time when the entire observable universe, every region of it without exception, was uniformly incapable of supporting anything resembling life. The first stars to form, sometimes called population 3 stars, were forged from this primordial gas, free of any heavy elements whatsoever, composed almost entirely of hydrogen and helium. These stars are thought to have been extraordinarily massive, far larger on average than the stars that form in the present-day universe, and correspondingly short-lived, burning through their fuel in a few million years before exploding as some of the most violent supernova the universe has ever produced. These first explosions were the universe's initial step toward chemical enrichment, scattering the very first heavy elements, the first carbon, the first oxygen, the first iron, into the surrounding gas. But a single generation of massive short-lived stars is far from sufficient to enrich an entire galaxy's worth of gas to the levels needed for substantial rocky planet formation. It took many subsequent generations, each one incorporating slightly more of the heavy elements produced by the generation before, gradually building up the chemical richness that the Milky Way's disk would eventually achieve by the time the solar system formed, roughly 9 billion years after the Big Bang. This means that the dead zone of the cosmic dark ages was not a localized hazard confined to a particular region of a particular galaxy, but a genuinely universal condition applying with equal force to every cubic light year of the observable universe. There was, quite literally, nowhere in the entire cosmos where life as we understand it could have existed during this period, not because of violence or radiation, but simply because the raw materials had not yet been manufactured anywhere. Thinking about this universal dead zone helps frame everything else we have discussed tonight in proper perspective. The various localized dead zones within galaxies, within clusters, within voids, are all variations and complications layered on top of this even more fundamental, even more universal early dead zone. The long, dark stretch of cosmic history during which the universe, everywhere, lacked the basic chemical prerequisites for the kind of complexity that life requires. From this universal early dead zone, let's trace the slow, uneven process by which different regions of the universe gradually emerged from chemical poverty at different rates. Because this unevenness is itself an important part of understanding why some regions of the present-day universe remain less favorable than others. Galaxy formation in the early universe was not a uniform, simultaneous process occurring identically everywhere. Some regions of the universe, generally the denser regions that would go on to form the cores of what are today massive galaxy clusters, began forming stars earlier and more vigorously than other, less dense regions. This means that the chemical enrichment process, the gradual buildup of heavy elements through successive stellar generations, also proceeded at different rates in different places, with the densest, earliest forming regions racing ahead in chemical maturity, while less dense regions lagged considerably behind. This unevenness has left a lasting imprint on the present-day universe. Some of the most chemically enriched stars known are found, somewhat counterintuitively, in the central regions of massive elliptical galaxies, precisely the kind of galaxy we identified earlier as facing its own habitability challenges due to the early exhaustion of its gas supply and the aging of its stellar population. These galaxies got a head start on chemical enrichment, racing through many generations of star formation in a relatively short period early in cosmic history, but then ran out of fuel for new star formation precisely because they used it up so quickly and so early. Meanwhile, galaxies like our own Milky Way, forming and enriching themselves more gradually over a longer period, achieved a kind of steady, sustainable chemical development, building up sufficient heavy element abundance for substantial rocky planet formation, while still maintaining an ongoing moderate rate of star formation billions of years later, providing a continuing supply of new, potentially planet-hosting stars throughout cosmic history, rather than concentrating all of that activity into an early burst, followed by billions of years of quiescence. This contrast between the early, rapid chemical enrichment of massive elliptical galaxies and the slower, more sustained enrichment of moderate spiral galaxies like the Milky Way illustrates one of the recurring themes of tonight's exploration: that habitability is rarely a simple matter of more being better or earlier being better. The galaxies that raced ahead fastest in chemical enrichment paid for that speed with an early exhaustion of their star-forming fuel, while the galaxies that developed more slowly and steadily, like our own, achieved a more balanced and, it appears, more genuinely sustainable trajectory toward long-term habitability. There is an additional wrinkle to this story involving a particular and very specific kind of dead zone that operates not at the scale of an entire galaxy, but at the scale of individual star systems, and it concerns the stars themselves rather than their surrounding galactic environment. The question of which kinds of stars are even capable of providing the long, stable energy output that complex life appears to require. We have, throughout tonight's exploration, generally assumed that any sufficiently chemically enriched, sufficiently undisturbed region of a galaxy provides a fair chance for habitability. But this glosses over an important additional requirement. The host star itself must be of a type capable of burning steadily for billions of years, providing the kind of long, stable energy output that the slow processes of biological evolution appear to require. The most massive stars, the very stars most responsible for producing dramatic supernovae and gamma-ray bursts, burn through their nuclear fuel extremely quickly, living for only a few million years before exploding, a timescale far too short for any planet orbiting them to develop complex life, even setting aside the additional hazard those same stars pose to their neighbors through their eventual explosive deaths. Any region of a galaxy dominated by an unusually large population of these short-lived massive stars is, in a sense, doubly disadvantaged for habitability. Not only do these stars pose an elevated supernova risk to their neighbors, but their own planets, if any form, simply do not have enough time before their host star's death to develop anything resembling complex life. At the other end of the stellar mass spectrum, the smallest, faintest stars, the red dwarfs that vastly outnumber sun-like stars throughout the galaxy, burn far more slowly and can persist for trillions of years, far longer than the current age of the universe. This would seem to offer an enormous advantage in terms of available time for biological evolution. But red dwarf stars present their own habitability challenges. Their habitable zones, the region where a planet's surface temperature could permit liquid water, lie much closer to the star than for a sun-like star, due to the red dwarf's lower overall luminosity. Planets orbiting this closely often become tidally locked, with one hemisphere perpetually facing the star and the other perpetually facing away, a configuration that may create severe climate challenges. Additionally, red dwarf stars are often considerably more magnetically active than sun-like stars, particularly during their youth, producing frequent and intense flares that could repeatedly strip away the atmospheres of any closely orbiting planets before life would have any reasonable chance to develop. Sun-like stars of intermediate mass occupy something of a middle ground here as well, much as the Milky Way's disk occupies a middle ground between the violent galactic center and the chemically poor outer halo. They burn steadily enough, and for long enough, roughly 10 billion years for a star of the Sun's specific mass, to provide the kind of extended, stable energy output that complex life appears to require, while avoiding both the catastrophically short lifespans of the most massive stars and the more severe flare activity and tidal locking challenges associated with the smallest red dwarfs. This stellar-scale habitable zone, nested within the galactic-scale habitable zone, nested within the still larger considerations of a galaxy's overall environment and history, adds yet another layer to the multi-scale picture of cosmic habitability we have been assembling tonight, reinforcing the broader pattern. That favorable conditions for life seem to cluster not at either extreme of any given parameter, whether stellar mass, galactic location, or cosmic environment, but somewhere in a moderate, balanced middle ground. Let's turn our attention, for a while, to a specific and well-studied example of a galactic dead zone that has been the subject of considerable astronomical research. The central molecular zone of the Milky Way, a region extending roughly a few hundred light-years from the galactic center, packed with extraordinarily dense concentrations of molecular gas and characterized by levels of star formation activity and turbulence far exceeding anything found in the quieter disk of the galaxy, where our own solar system resides. The central molecular zone is, in many respects, a microcosm of everything that makes the broader galactic center hazardous for habitability, condensed into a relatively compact region. The gas here is subjected to intense tidal forces from the nearby supermassive black hole, intense magnetic fields, and frequent collisions between massive molecular clouds, producing conditions of turbulence and energy input far beyond what is found in more typical star-forming regions elsewhere in the galaxy's disk. Stars that do form within this environment face an unusually hazardous upbringing. The intense radiation field produced by the dense concentration of young, massive stars already present in the region can photo-evaporate the protoplanetary disks of any newly forming stars before they have the chance to fully form planets, stripping away the gas and dust that would otherwise coalesce into planetary bodies. Even where planets do successfully form, they would face the ongoing hazards we have already discussed. An elevated rate of nearby supernovae due to the high concentration of massive stars, an elevated background of high-energy radiation from the nearby active galactic center, and a generally more chaotic gravitational environment due to the sheer density of nearby stellar neighbors. Astronomers studying this region have found that, despite its hostility to long-term habitability, it remains a remarkably productive region for the formation of new stars, simply because the raw density of available gas is so much higher than elsewhere in the galaxy. This creates an interesting tension. The central molecular zone may be one of the most prolific star-forming regions in the entire Milky Way, producing new stars at a disproportionately high rate relative to its small size, while simultaneously being one of the least hospitable regions for any of the planets that might form around those stars to develop into long-term habitable worlds. This tension between productivity and habitability, between a region's capacity to form new stars and planets and that same region's capacity to allow those planets to develop into stable, long-term habitable environments, is a recurring and important theme that complicates any simple assumption that more star formation activity automatically translates into more opportunities for life. Sometimes, as in the case of the central molecular zone, the very conditions that drive elevated star formation, intense gravitational compression, high gas density, frequent cloud collisions, are the same conditions that make the resulting planetary systems unusually hazardous places for life to develop. There is another dimension to this discussion that deserves careful attention: the role of a galaxy's spiral arm structure itself, not just as a source of elevated star formation and associated supernova risk, but as a dynamic, evolving feature that interacts with a star's orbit around the galaxy in complex and only partially understood ways. Spiral arms are not static, fixed structures rotating rigidly along with the stars within them. Instead, they are understood, in the most widely accepted models, to be density waves, patterns of enhanced stellar and gas density that propagate through the galactic disk at a different rate than the orbital speed of individual stars. This means that a star like our Sun does not remain fixed within a spiral arm, nor does it simply orbit alongside the arm's structure. Instead, stars periodically catch up to, pass through, and eventually exit spiral arms as their own orbital motion and the pattern motion of the spiral structure interact over time. This has interesting implications for our understanding of the Sun's own history and its passage through different galactic environments over its roughly 4.5 billion-year existence. Some researchers have proposed that the Sun's orbit may have carried it through one or more spiral arm crossings since the solar system's formation, each crossing representing a period during which the local density of young, massive, short-lived stars and the associated supernova risk would have been elevated above the longer-term average for the Sun's orbital path. If such crossings have indeed occurred, they would represent temporary excursions into a somewhat less favorable galactic environment, periods of elevated risk nested within an overall orbital history that has, fortunately, avoided any catastrophic civilization-ending event throughout the entire span of life's development on Earth. Some researchers have looked for correlations between proposed spiral arm crossing events and patterns in the geological and paleontological record, including the timing of mass extinction events. Though, as mentioned earlier, this remains a contested and still developing area of research rather than a settled scientific conclusion. What this does illustrate, regardless of how the specific correlations with Earth's biological history ultimately hold up, is an important general principle. A star's position relative to the galactic dead zones we have discussed tonight is not necessarily fixed for the star's entire lifetime. Just as the Galactic Habitable Zone itself shifts and evolves over the history of the galaxy, an individual star's specific location relative to the safer and more hazardous regions of the galaxy can change over time as the star's orbit carries it through different galactic environments, sometimes into closer proximity with elevated hazards, and sometimes back out into quieter, safer territory. Let's spend some time now considering a related question that connects the structure of cosmic dead zones to the broader search for technologically advanced civilizations elsewhere in the universe, sometimes discussed under the heading of the Fermi Paradox, the apparent tension between the vast number of stars and potentially habitable planets in the galaxy, and the complete absence, so far, of any confirmed evidence for extraterrestrial intelligence. Among the many proposed explanations for this apparent silence, one category of explanation draws directly on the concept of cosmic dead zones that we have been exploring tonight. If the requirements for a planet to develop not just simple life, but complex, eventually intelligent and technologically capable life are considerably more stringent than the requirements for simple life alone, requiring an unusually long, undisturbed window of stability stretching across billions of years, then the effective habitable zone for the development of intelligent civilizations specifically might be considerably smaller and more restrictive than the broader habitable zone for life in general. This idea, sometimes discussed under the heading of the rare Earth hypothesis, suggests that while simple microbial life might be relatively common throughout the galaxy, arising readily wherever the basic chemical and energetic prerequisites are met, the development of complex, multicellular, and eventually intelligent life might require such an unusually long and unusually undisturbed sequence of favorable conditions, avoiding not just any single catastrophic sterilization event, but the entire cumulative history of smaller disruptions that could repeatedly set back or entirely halt the slow climb toward biological complexity. That truly intelligent life might be vanishingly rare, even in a galaxy otherwise teeming with simpler forms of life. Under this view, the various dead zones we have explored tonight, the crowded galactic center, the chemically impoverished outer halo, the hazardous environment near active galactic nuclei, the periodic risk of nearby supernova as a star's orbit carries it through different galactic environments over billions of years, function collectively as a kind of extended filter, progressively narrowing down the much larger population of planets capable of hosting simple life to a much smaller subset of planets capable of supporting the kind of multi-billion-year, relatively undisturbed developmental window that complexity and intelligence appear to require. This remains, like several of the other ideas we have discussed tonight, a genuinely open and actively debated area of research, with reasonable scientists holding a wide range of views about just how restrictive these requirements actually turn out to be in practice. But it offers one more way of connecting the specific, detailed picture of cosmic dead zones we have built tonight to one of the largest and most profound open questions in all of science: whether we are, in some meaningful statistical sense, alone in the galaxy or surrounded by a quiet abundance of life that has simply not yet had the chance, or perhaps the means, to make its presence known to us. There is a thought worth holding here, gently, about the relationship between rarity and value, because it bears directly on how we might choose to feel about the picture of cosmic dead zones we have assembled across this long evening. If the requirements for complex, long-lived, biologically rich worlds like Earth turn out to be as restrictive as some of the considerations we have discussed tonight suggest, requiring a fortunate confluence of favorable conditions across multiple scales simultaneously, sufficient chemical enrichment, sufficient distance from violent galactic centers, a host star of the right mass and stability, an undisturbed multi-billion-year window free from any galaxy-wide sterilizing catastrophe, then worlds like our own may be considerably rarer, in a strict statistical sense, than a casual glance at the sheer number of stars and planets in the universe might initially suggest. This rarity, rather than diminishing the significance of our own existence, can be understood as deepening it. A common, easily replicated outcome carries a certain kind of significance, the significance of being one example among countless similar examples, each unremarkable in its individual specificity, precisely because so many others like it exist. A rare outcome, by contrast, carries a different kind of significance, the significance of being a genuinely unusual and hard-won result emerging from a long, improbable sequence of favorable circumstances that did not have to align as they did, and that may not have aligned in quite the same way anywhere else within the observable universe, or at least not very often. This is not a claim that we are necessarily unique in the sense of being the only place in the universe where life has developed. The universe is large enough and the number of stars and planets vast enough that even genuinely rare outcomes are likely to be replicated somewhere simply due to the scale of the available opportunities. But it is a recognition that our own specific instance of that outcome, the specific planet, the specific biosphere, the specific multi-billion-year history of relatively undisturbed development that has led to this particular moment. With you resting here, thinking about these very questions represents something that the universe does not produce casually or automatically everywhere it has the chance. It produces it carefully, rarely, and only under a fairly specific and demanding set of circumstances. Carrying that recognition, not as a source of anxious uniqueness, but as a quiet, settled appreciation for how genuinely improbable and how genuinely precious the specific outcome of your own existence actually is, feels like an appropriate note to carry forward as we continue toward the close of tonight's exploration. Let's turn, for a few more minutes, to the question of how astronomers actually go about measuring and quantifying the hazards we have discussed tonight, because the methods involved are themselves an interesting part of this story, much as they were in our previous explorations of the cosmic web and the large-scale flows of galaxies. Measuring the chemical enrichment of different regions within a galaxy, The basic metallicity gradient that determines how favorable different locations are for substantial rocky planet formation relies on detailed spectroscopic observations of individual stars, measuring the strength of specific absorption lines in their spectra that correspond to the presence of particular heavy elements like iron, calcium, and magnesium. By measuring these spectral signatures for large samples of stars at different distances from the galactic center, astronomers have been able to map out the metallicity gradient of the Milky Way's disk in considerable detail, confirming the general pattern of increasing chemical enrichment moving inward from the metal-poor outer halo toward the more enriched inner disk, before the trend reverses again in the immediate vicinity of the chaotic and complicated galactic center itself. Measuring the rate of supernovae and their associated hazards relies on a combination of direct observation of supernovae in other similar galaxies, allowing astronomers to estimate the overall rate at which these events occur per unit of stellar mass or per unit of star formation activity, combined with theoretical models of how the radiation and particle output from a given supernova would propagate through interstellar space and interact with a planet's atmosphere at varying distances. Combining these observational rate estimates with the theoretical models of biological hazard allows researchers to estimate the overall background risk faced by a planet at any given location within a galaxy, based on the local density of massive supernova progenitor stars in that location. Mapping the large-scale distribution of galaxy clusters, voids, and the broader cosmic web relies on the same kinds of large redshift surveys we explored in detail in a previous episode, measuring the distances and positions of hundreds of thousands or millions of galaxies to build up a three-dimensional map of the universe's large-scale structure, from which the locations of crowded cluster environments, quiet filaments, and vast, underdense voids can be directly identified and characterized. And modeling the overall historical arc of cosmic chemical enrichment and habitability, the long curve from the early universe's near-total inhospitality through to whatever peak of favorability the universe may eventually achieve, relies on sophisticated computer simulations that attempt to model the entire history of star formation, supernova feedback, and chemical enrichment across cosmic time, calibrated against the observed properties of galaxies at different distances and therefore different ages throughout the observable universe. Each of these methods, like the methods we explored in our discussion of the Great Attractor and the cosmic web more broadly, requires painstaking observational work, careful calibration, and sophisticated statistical and computational analysis to extract a clear signal from what is often a noisy and complicated underlying reality. The map of cosmic dead zones and habitable zones that we have explored tonight, woven together from many different lines of evidence and many different observational techniques, represents a genuinely impressive achievement of patient, careful, collaborative scientific work, even as significant uncertainties and open questions remain in many of the specific details. As we move toward the final stretch of tonight's exploration, let's consider one more facet of the cosmic dead zone concept, one that brings us back, in a sense, to where we began. The question of how this entire picture might continue to evolve and develop as our observational capabilities continue to improve in the coming years and decades. The next generation of large astronomical surveys, the kind of comprehensive wide-field projects we have mentioned in previous explorations, promises to dramatically expand our ability to map the detailed chemical composition, stellar density, and overall environmental hazard profile of regions throughout the Milky Way, and increasingly in other nearby galaxies as well. Surveys capable of measuring the detailed chemical abundances of millions of individual stars across the galaxy's disk and halo will allow astronomers to refine the boundaries of the galactic habitable zone with far greater precision than has been possible to date, moving beyond the broad general picture we have sketched tonight toward a much more detailed and nuanced map of exactly which regions of the galaxy's disk offer the most favorable balance of chemical enrichment and protection from violent hazards. Similarly, ongoing and future surveys of exoplanets around stars at a wide range of galactic locations, from the metal-poor outer halo to the denser, more chemically enriched inner disk, will gradually allow researchers to test the predictions of the Galactic Habitable Zone concept directly, comparing the actual observed frequency of potentially habitable rocky exoplanets across these different environments against the theoretical expectations we have discussed tonight, built up from our understanding of stellar and galactic chemistry. There is also considerable ongoing work attempting to better understand and quantify the various violent hazards we have discussed, refining our estimates of how frequently gamma-ray bursts and supernovae actually occur in galaxies of different types and different chemical compositions, and developing more detailed and more reliable models of exactly how the radiation and particle output from these events would interact with a planet's atmosphere and biosphere at varying distances, building on the foundational work that first identified these hazards as significant factors in the overall habitability picture. And at the very largest scales, ongoing efforts to map the cosmic web in ever greater detail, identifying the precise boundaries and properties of galaxy clusters, filaments, and voids throughout an increasingly large volume of the observable universe, will continue to refine our understanding of how a galaxy's broader cosmic environment, isolated void, quiet filament, or crowded cluster core, influences its own internal capacity to host long-term habitable worlds. Taken together, these ongoing and future research efforts promise to transform the picture we have built tonight from a largely theoretical framework, grounded in solid physical principles, but still relying heavily on extrapolation and modeling, into an increasingly detailed, increasingly empirically grounded map of exactly where, throughout the Milky Way and beyond, the universe's dead zones and habitable zones actually lie, and exactly how favorable or unfavorable our own specific cosmic address actually is relative to the full range of possibilities the universe has produced. Let's allow ourselves, for a few final moments, to sit with the full sweep of everything we have covered tonight, drawing the many separate threads together into something more like a single, coherent picture. We began with the recognition that habitability is not a simple binary property, present or absent, but a graded, multi-scale phenomenon shaped by an enormous range of interacting factors operating from the scale of an individual planet's distance from its star all the way up to the largest structures of the cosmic web. We explored the Galactic Habitable Zone, the band within a galaxy's disk that balances sufficient chemical enrichment against sufficient distance from the violent, crowded galactic center. We explored how this balance shifts and evolves over the long history of a galaxy's chemical enrichment, expanding and changing shape as successive generations of stars seed the surrounding gas with the heavy elements life requires. We explored the differences between galaxies of different types and sizes, finding that both very small, chemically impoverished dwarf galaxies and very large, early-forming, gas-exhausted elliptical galaxies face their own distinct challenges to long-term habitability, while moderate, ongoing star-forming spiral galaxies like our own Milky Way occupy something of a favorable middle ground. We explored the hazards associated with crowded galaxy cluster environments, where gas stripping, frequent galaxy interactions, and proximity to some of the most energetic active galactic nuclei in the universe combine to create a genuinely hostile environment for the long-term development of stable planetary systems. We explored the specific violent hazards of gamma-ray bursts and supernovae, and how their frequency has changed over cosmic time as the universe's overall chemical composition has evolved. We explored the persistent background hazard of cosmic rays and the more exotic and more uncertain possibility of galaxy-wide sterilization events triggered by unusually intense bursts of central activity. We explored the paradoxical safety and chemical poverty of the great cosmic voids and the early, near-universal dead zone of the cosmic dark ages, before the first generation of stars had even begun the long, slow process of chemical enrichment that would eventually make worlds like our own possible. And throughout all of this exploration, we returned again and again to the specific, fortunate reality of our own situation. A planet orbiting a stable, long-lived, moderate-mass star in a quiet, chemically enriched spiral arm within a galaxy that has sustained a steady, ongoing rate of star formation across billions of years without prematurely exhausting its fuel, situated in a modest galactic neighborhood far from the crowded and hazardous core of any rich cluster, existing at a moment in cosmic history favorable enough, but not yet at whatever far future peak the universe's overall habitability may eventually reach. There is one final reflection worth offering before we let this long evening's exploration settle fully into rest, and it concerns the relationship between knowledge and comfort, between understanding the genuine scale of cosmic hazard that surrounds our own fortunate circumstances and finding, within that understanding, a source of peace rather than anxiety. It would be entirely understandable if tonight's exploration of the universe's many dead zones, the violent galactic centers, the chemically impoverished voids and outer halos, the crowded and hazardous cores of galaxy clusters, the ever-present background risk of supernovae and gamma-ray bursts, left you with a heightened sense of how fragile and how contingent our own favorable circumstances actually are. This would be a reasonable response to the material we have covered, and it would not be incorrect. But there is another way to receive this same information, one that I would gently offer as we close. The fact that the universe contains so many ways of being hostile to life, and that our own specific corner of the cosmos has, against this vast backdrop of potential hazard, remained stable and favorable for the entire multi-billion-year history of life's development here, can be understood not as evidence of fragility, but as evidence of a kind of deep, quiet resilience built into the actual circumstances of our existence. We are not perched precariously on the edge of catastrophe, anxiously awaiting the moment when one of these cosmic hazards finally reaches us. We are, rather, settled comfortably within a genuinely stable, genuinely favorable environment, one that has already demonstrated across billions of years and through the natural history of an entire biosphere's development that it possesses exactly the kind of long-term stability that the patient unfolding of life requires. The dead zones are real, and they are vast, and they occupy, by any reasonable accounting, the majority of the universe's volume and the majority of its history. But they are not where we are. We are somewhere else, somewhere quieter, somewhere more fortunate, somewhere that has already proven, through the simple ongoing fact of our own existence and the existence of everything alive around us, that it belongs to the much smaller, much rarer category of places the universe has made genuinely safe for the long, slow work of becoming complex, becoming aware, becoming capable of looking outward and understanding with real clarity just how remarkable that safety actually is. The night has grown quiet now, and the long landscape of cosmic hazard and cosmic safety that we have explored together this evening can settle gently into the background of your awareness, where it belongs, not as an active worry, but as a quiet, settled piece of context for understanding just how specific and just how fortunate your own existence within the universe's vast structure actually is. Somewhere out there, hundreds of thousands of light years toward the galactic center, conditions remain too violent, too crowded, too chemically immature in some sectors, and too chemically exhausted in others for the kind of long, patient development that has unfolded here, undisturbed, for billions of years. Somewhere out there, in the crowded cores of distant galaxy clusters, the relentless stripping of gas and the constant gravitational churn make stable, long-term planetary systems a genuine rarity. Somewhere out there, in the vast, quiet emptiness of the great cosmic voids, the raw chemical ingredients for a world like our own remain too sparse, too slowly accumulated for life as we know it to have much of a foothold. And here, in this specific, modest, comfortably favorable corner of an ordinary spiral galaxy, none of those hazards apply, not because the universe owed us this safety, but because the long, patient, improbable unfolding of cosmic history happened to produce in this one particular location exactly the conditions that the slow chemistry of life requires. You are resting right now in one of the universe's genuinely rare safe harbors. The dead zones stretch out beyond you in every direction, vast and largely indifferent, but they are not here. Here, the conditions are gentle. Here, the chemistry has had its billions of years. Here, you can simply rest safely within the quiet, fortunate exception that your own existence represents. If this long, slow journey through the universe's hidden landscape of hazard and safety has given you something worth carrying into sleep, a quiet appreciation for just how specific and just how fortunate your own corner of the cosmos actually is, you are welcome to return to Beyond the Cosmos whenever you would like to explore further. The universe is patient, and so are we, and there is always another layer of this landscape waiting to be explored together. For now, let your breathing slow, let the weight of the day finally release, and let the quiet, settled knowledge of your own fortunate place in the universe carry you gently toward rest. Good night. Before we let the night fully take over, there is one more strand of this story that deserves attention because it brings the discussion back to something we touched on briefly earlier but did not fully unpack. The role of a planet's own magnetic field and atmosphere in determining how severely it experiences whatever background hazards its galactic neighborhood happens to present. A planet does not face the radiation environment of its surroundings passively. Earth, for instance, possesses a strong global magnetic field generated by the churning motion of molten iron in its outer core that deflects a substantial fraction of incoming charged particles, including much of the steady stream of cosmic rays and solar wind that would otherwise reach the surface directly. This magnetic shielding, combined with a thick atmosphere that further absorbs and scatters incoming radiation before it reaches ground level, means that Earth experiences a considerably gentler radiation environment at its surface than the raw, unshielded flux arriving from space would suggest. This matters enormously for how we think about the dead zones we have discussed tonight, because it means that a planet's own internal properties, the strength of its magnetic field, the thickness and composition of its atmosphere, can partially compensate for an otherwise hazardous galactic location. Or, conversely, a planet with a weak magnetic field and a thin atmosphere could find itself considerably more vulnerable to hazards that a better shielded world in the same location would weather without serious consequence. This adds an important qualifier to everything we have explored tonight about the spatial distribution of cosmic hazards. The Galactic Habitable Zone, the safer regions away from crowded clusters, the more chemically mature areas of a galaxy's disk, all of these describe the background environment a planet finds itself in, but they do not fully determine that planet's actual experience of that environment. A well-shielded planet in a moderately hazardous location might fare better, in practice, than a poorly shielded planet in a nominally safer one. Habitability, once again, reveals itself to be a layered compound property, dependent not just on where a planet is, but on what that planet itself brings to the encounter with its surroundings. This is, in its own way, a hopeful complication. It suggests that the strict boundaries we have drawn tonight between favourable and unfavourable cosmic environments are not absolute walls, but more like gradients of probability, where a planet's own protective properties can shift its individual chances somewhat, even within a galactic neighbourhood that, on average, presents elevated risk. The universe's dead zones are real, but they are not entirely deterministic. Within even a relatively hazardous region, an unusually well-protected world might still find a way to maintain the long, stable conditions life requires, just as, conversely, a poorly shielded world in an otherwise favourable location might face greater vulnerability than its location alone would suggest. Let's also take a moment to consider how the concept of cosmic dead zones connects to the broader question of planetary atmospheres and their long-term stability against erosion, because this turns out to be deeply intertwined with several of the hazards we have already discussed. When a planet is exposed to an elevated flux of high-energy radiation, whether from a nearby supernova, an unusually active host star, or the more energetic environment near an active galactic nucleus, one of the most significant long-term consequences is the gradual erosion of that planet's atmosphere. High-energy particles and radiation can ionize atmospheric molecules, providing them with enough energy to escape the planet's gravitational pull entirely, a process that, over sufficiently long timescales, can strip away a substantial fraction of a planet's original atmospheric inventory. This connects the various dead zones we have discussed tonight to a single unifying mechanism: atmospheric loss. A planet near the crowded galactic center faces elevated atmospheric erosion from the more energetic radiation environment there. A planet near an unusually active host star, particularly one of the small, magnetically active red dwarfs we discussed earlier, faces elevated atmospheric erosion from frequent stellar flares. A planet within a crowded galaxy cluster exposed to the energetic environment of a nearby active galactic nucleus faces its own version of this same fundamental hazard. In each case, the specific source of the radiation differs, but the underlying threat to long-term habitability is broadly similar. Without a sufficiently thick atmosphere to provide insulation, regulate temperature, and shield the surface from the worst of incoming radiation, even a planet that is otherwise well-positioned in terms of its distance from its star will struggle to maintain the kind of stable surface conditions that the long, patient development of life appears to require. This is part of why Earth's own retention of a substantial atmosphere across billions of years, aided by its strong magnetic field and its location in a relatively quiet, undisturbed galactic environment, represents such a significant and, in a strict statistical sense, fortunate achievement. Many planets throughout the universe, even those that might otherwise sit within a star's traditional Goldilocks zone, may have lost the bulk of their original atmospheres long before life had any meaningful chance to develop, victims of exactly the kind of radiation hazards that the various dead zones we have explored tonight represent. As we draw close to the true end of tonight's exploration, let's consider, briefly, what all of this might mean for the broader human project of understanding our place in the universe, a project that this very channel exists to explore, one slow, careful evening at a time. For most of human history, the question of our cosmic situation was approached through myth, through philosophy, through religious tradition, each offering its own account of why the world exists as it does, and what role, if any, human beings occupy within that larger order. The scientific picture we have built tonight offers a different kind of account, grounded not in narrative or revelation, but in careful measurement, in spectroscopy and redshift surveys and computer models of galactic chemical evolution. And yet it arrives, in its own way, at a conclusion that carries genuine emotional and even spiritual weight. That our existence here, on this particular planet, in this particular galaxy, at this particular moment in cosmic history, reflects an improbable, hard-won convergence of favorable circumstances, stacked carefully across multiple scales, that the universe does not produce casually or universally, but rarely, and with what might reasonably be called a kind of cosmic care, even though we know that care in this context is simply the patient, indifferent unfolding of physical law rather than any conscious intention. This is, I think, one of the great gifts that careful scientific exploration of the universe can offer. Not a replacement for the older traditions of meaning-making, but a complement to them, a way of grounding our sense of wonder and gratitude in something concrete, measurable, and real. We do not need to imagine or speculate about whether our existence is special. We can trace, with genuine scientific precision, the specific chain of circumstances, chemical, gravitational, radiative, that had to align in just the right way, across billions of years and at every scale from the individual star to the largest structures of the cosmic web, for a planet like Earth and a creature like you, listening to these words in the quiet of your own evening, to come into being. That is not a small thing. It is, in fact, about as large a thing as the human mind can hold, and yet it arrives here at the end of this evening's exploration, not as an overwhelming weight, but as something closer to a gentle, settling comfort. The universe is vast, and much of it is hostile, and against that vast backdrop, you exist, here, now, safely, within one of its rare and genuine exceptions. Let the final image of tonight be a simple one, returning to where we began, but carrying with it now the full weight of everything we have explored together across this long and careful evening. You, wherever you are right now, in your bed, in your chair, beneath whatever sky happens to stretch above your particular corner of the world tonight, are located within a specific, identifiable, and genuinely rare region of cosmic favorability. Behind you, in cosmic terms, lies the long, dark stretch of the universe's earliest history, when no life anywhere was possible because the basic chemical ingredients had not yet been made. Around you, at every scale, from the structure of your own galaxy to the largest superclusters of the cosmic web, lie vast regions where violence, chemical poverty, or both would make the patient unfolding of biological complexity difficult or impossible. And yet, here you are, resting safely within the quiet, fortunate exception that your own existence represents. The universe has a dead zone. In truth, as we have explored tonight, it has many dead zones, nested within each other, distributed across every imaginable scale, from the crowded heart of our own galaxy to the largest voids of the cosmic web, from the earliest, chemically barren moments after the Big Bang to whatever far future fading awaits the cosmos once its long supply of star-forming gas is finally exhausted. And scattered rarely against this vast and largely hostile backdrop are the quiet exceptions, the favorable corners, the places where chemistry has had its time and violence has kept its distance, long enough for something as intricate and as improbable as a thinking, feeling, resting creature to come into being. You are one of those exceptions, not through any effort or choice of your own, but through the long, patient, careful unfolding of cosmic history that placed a small, modest, comfortably enriched corner of the universe exactly where it needed to be, for exactly long enough for you to exist here now safely within it. If tonight's exploration of the universe's hidden landscape of hazard and safety has given you something quiet and good to carry into sleep, you are always welcome back at Beyond the Cosmos. The questions never run out, and neither does the curiosity that brings us, again and again, to sit with them together. Rest now. You are exactly where you need to be. Good night. There is one last consideration worth folding into tonight's exploration before we close, and it concerns the way astronomers think about probability and uncertainty when discussing something as consequential and as difficult to test directly as the overall habitability of different cosmic environments. Almost everything we have discussed tonight involves a degree of genuine scientific uncertainty. We know, with high confidence, that chemical enrichment varies across a galaxy's disk, and we know, with similarly high confidence, that supernovae and gamma-ray bursts release dangerous radiation capable of damaging a planet's atmosphere at sufficiently close range. But translating these well-established individual facts into a confident, detailed map of exactly which regions of the universe are and are not capable of supporting life requires combining many different lines of evidence, each with its own uncertainties, into a single coherent picture, and reasonable researchers sometimes disagree about exactly how to weigh and combine these different factors. This is not a weakness of the science, but a natural and expected feature of working at the frontier of what is currently knowable. The picture we have built tonight of a universe textured with favourable and unfavourable zones at every scale is well supported by the underlying physics and by a substantial and growing body of observational evidence. But the precise boundaries of these zones, exactly how close is too close to a galactic centre, exactly how isolated is too isolated within a cosmic void, exactly how much chemical enrichment is sufficient for a reasonable chance at rocky planet formation, remain subjects of active research and ongoing refinement. This uncertainty is, in its own way, part of what makes this subject so genuinely exciting to explore. We are not simply reciting settled facts tonight. We are walking through the current frontier of an active, unfolding scientific investigation, one that is being refined and sharpened with every new survey, every new exoplanet discovery, every new computational model of galactic chemical evolution. The picture will look somewhat different, somewhat more detailed and somewhat more precisely calibrated a decade from now, and different again a decade after that, as the tools and the data continue to improve. Holding this uncertainty alongside the confidence we can reasonably place in the broad outlines of the picture, the basic existence of galactic dead zones shaped by chemistry and violence, the basic existence of cosmic-scale dead zones shaped by cluster environments and void isolation, the basic arc of the universe's overall habitability rising from a chemically barren youth towards some future peak before eventually fading again, feels like the right way to close this particular evening's exploration. We know enough to understand, with genuine confidence, that our own situation is favourable and, in a meaningful statistical sense, rare. We do not yet know everything about exactly how rare or exactly what the full detailed map of the universe's habitability looks like. And that remaining uncertainty is not a gap to be anxious about, but an invitation for those who find this kind of exploration compelling to keep paying attention as the picture continues to sharpen in the years ahead. And so we arrive, finally, at the close of tonight's long, slow journey through the universe's hidden landscape of hazard and safety. We have traveled from the crowded, violent heart of our own galaxy outward through its quieter disk, out further still into its chemically impoverished halo. We have traveled across the boundaries of entire galaxies, comparing the chemical fortunes of dwarfs and giants, spirals and ellipticals. We have descended into the crowded, hazardous cores of rich galaxy clusters, and out again into the vast, quiet emptiness of the cosmic voids. We have traced the universe's slow chemical maturation from its earliest, barren beginnings toward whatever distant peak of habitability the far future may hold. And throughout all of that traveling, we have returned again and again to this single, quiet, comfortably favorable point. Here, on this planet, in this moment where you are resting now. The universe's dead zones are vast, and they are real, and they occupy, by any honest accounting, the overwhelming majority of the cosmos across both space and time. But they are not where you are. You are somewhere else, somewhere rarer, somewhere the long, patient unfolding of cosmic history decided, for reasons rooted in nothing more mysterious than chemistry and gravity and time, to make gentle. Let that gentleness hold you now. Let the vast, indifferent landscape of cosmic hazard recede into the quiet background where it belongs, a fact to be known and appreciated rather than feared. You are not adrift in that hostile landscape. You are settled, safely, within one of its rare and precious exceptions, exactly as you have been for your entire life, exactly as the Earth has been for billions of years before you arrived. Beyond the cosmos will be here whenever you would like to explore further, whenever curiosity calls you back to sit with another of the universe's great questions. For tonight, there is nothing more to do but rest, here, in this gentle corner of an otherwise vast and demanding cosmos. Good night. One small, closing thought before the silence takes over completely. Every dead zone we have explored tonight, every hazard, every void, every crowded and violent corner of the cosmos exists for a reason rooted in the same basic physics that also produced the gentleness of your own circumstances. Gravity, chemistry, the slow burn of stars, the patient accumulation of heavy elements across billions of years, all of it operating according to the same universal laws everywhere, producing harshness in some places and, by the same token, gentleness in others. There is no separate rulebook for the favorable corners of the universe. The same processes that built the dead zones built your home as well, simply arranged in this one specific place into a configuration that happened to favor patience over violence, abundance over poverty, calm over chaos. That is, perhaps, the quietest and most settling thought of all. You are not an exception to the universe's laws. You are one of their gentlest possible outcomes, carefully, slowly, patiently assembled from the very same physics that elsewhere produces emptiness and hazard. Let that thought rest alongside you tonight. Good night.